So recently, NASA shared an image that made a lot of smart people sit up straight, not because it showed a sci-fi wall at the edge of everything, but because of what it implied. The farthest faint dots in that field look too early, too bright, too built. You see that, and your first thought is this: did we just find the edge of the universe? And then the next question hits even harder. Why does that edge seem to move? Let us talk straight. There are two ideas tangled up whenever people say edge of the universe. One is simple, the edge of what we can see. The other is bigger, the edge of what exists. Those are not the same thing. NASA did not photograph a brick wall at the end of reality. What they did was push our sightline farther than it has ever been and catch galaxies from a time that feels almost impossible. And as weird as it sounds, the boundary of what we can see really does move. Not because we are flying through space to meet it, but because space itself is stretching, and more ancient light keeps arriving as time passes. First thing first, how can you even talk about an edge when the universe has no outside? Think about it like this. Light has a speed limit. It takes time to get from there to here. The cosmos has only been shining for so long. That means you and I can only see out to a certain radius past that. There's not been enough time for light to reach us. That radius is the edge of the observable universe. The key word is observable, not the edge of existence. The edge of what has had time to announce itself. Now here is where it gets wild. You might think the farthest thing we can see should be about as far as light can travel in the age of the universe. Like the universe is about 14 billion years old, so the edge should be about 14 billion light years away. That would be true in a static universe. But the space between points has been expanding the whole time. While that ancient light was on the road itself stretched. So the farthest stuff we can see today is way farther than 14 billion light years in the sense of current distance. The number is larger, much larger. You do not need the exact value to get the point. The point is this: the edge of what we can see is not a circle we run up to. It is a horizon that sits out there because of time and expansion, and it shifts with us. So why did people say the new image broke physics? Because inside that field, astronomers flagged tiny smudges that were not supposed to be there in that abundance or with that brightness so early after the Big Bang. These things looked like mature galaxies and maybe even monster black holes living in a universe that was supposed to still be in its cosmic newborn stage. Our best model said you could have stars that early, sure, but not whole well-organized city-sized structures everywhere you look. So the reaction was not NASA found a wall, it was whoa. The timeline is tighter and busier than we thought. Let me give you an audio version of what that deep image looks like, because you are hearing me, not staring at a screen. Imagine a patch of sky that to the naked eye would look empty. Point a powerful space telescope at it and let it stare for a long time. The black fills with thousands of faint glints. Some are sharp and blue and nearby. Others are stretched and reddish, because their light has been dragged to longer wavelengths by the expansion of space. Those tiny red dots of the story, every one of them is a whole galaxy, not a star, a galaxy. And the most distant of those dots started shining when the universe was only a few 100 million years old. That is the first billion years of cosmic history, the construction zone. Now, a direct point that everyone needs to hear: the edge is moving. People always ask how that can be without breaking relativity. Here's the clean answer. Nothing is blasting through space faster than light. The space between things is growing. The metric of the universe, the yardstick itself, is stretching. That lets distant galaxies recede from us at an effective speed that can be faster than light without any rule being broken, because no object is outracing light in its local space. The result for us is two horizons that matter. There is the particle horizon, which is the farthest distance from which light has had time to reach us since the beginning. That one grows as time passes because more ancient light arrives. And there is the event horizon, which is the farthest distance today from which light sent now will ever reach us in the future. That one sets a hard boundary for future conversations with the cosmos. So yes, the edge we can see moves. The ultimate boundary of who we can ever talk to is fixed by the expansion rate and the weird pressure of the vacuum. Do not worry. We will keep this grounded and not drift into buzzwords. Think about redshift. It is the way the color of light slides toward the red end as the universe expands. That redshift is the clock we use to tell how far back we are looking. Bigger redshift means earlier time and farther comoving distance. When NASA teams point the telescope at a deep field and you hear they found record redshift galaxies, that means we just pushed the timeline farther back. And when you look at a field like that, there is a second thing going on that people forget. Gravity can bend light, that is gravitational lensing. A fat cluster of galaxies in the foreground can act like a magnifying glass. It bends and stretches light from even more distant galaxies behind it, so those background galaxies look like thin arcs and are easier to spot. That is how we sometimes get a peek at the truly extreme edge of what is visible. The glassing effect of gravity, quick audio description for listeners. When we talk about a lensing image, in a cluster lens, you would see a bright knot of many galaxies in the middle, like a city skyline. Around that core, you would hear me describe delicate arcs and streaks wrapping partway around the center. Those arcs are not smears from a shaky camera. They are background galaxies being warped by gravity. Even if you never see the picture, you can understand the geometry from that description. Mass in the middle, arcs around it, background light bent into a curve. Let us circle back to the thing everyone wants to know. If the edge moves, will we ever see the true end? Probably not in the way people imagine. There is no cliff where stars give way to nothing. The universe does not need an outside. If it is finite, it could wrap in a shape that has no edge, like the surface of a sphere has no edge, even though it is finite. If it is infinite, then any edge talked beyond our horizon is simply not meaningful. What we do have is a cosmic fog bank. The earliest light we can ever see directly is from a time when the whole universe turned transparent for the first time. Before that, space was a glowing plasma that scattered light like milk. The moment it cleared, light could fly free, and we still detect that glow today as a faint microwave afterglow spread across the whole sky. That is the oldest light. That is our baby picture. That is a kind of edge, not an end of space, an end of what photons can tell us directly. Here is an audio description for that map, because most people have only seen it as a colorful oval. If you could see this with your ears, it would be a full sky heat map, where tiny temperature differences show up as patches, warmer and cooler by a fraction of a degree. The pattern is not random noise. It has a very specific scale. That scale tells us about how the early universe rang like a bell from that pattern. Scientists pull out numbers like the age, the composition, and how flat the geometry is on large scales. Even if you never look at the picture, the description gives you the punchline. The baby universe had tiny ripples. Those ripples grew into the web of galaxies we see now. So, what exactly in the new image got people fired up? You had candidates for galaxies at extreme redshift that looked too beefy and too common. The takeaway is not that physics is broken and we throw out the laws. It is that our story about how fast the first stars and black holes formed might need tuning. Maybe stars were more efficient at turning gas into light in those environments. Maybe heavy elements and dust built up faster than we assumed. Maybe black holes got a head start by collapsing from dense gas rather than only growing from dead stars. These are not cheats. They are knobs in the story that data helps us set. Now let us address the cliffhanger headline that always shows up. We found the edge and it is moving. Here is the clean version you can tell a friend without sounding like you ate a textbook. The edge you care about is the farthest stuff whose old light has arrived here. As the years pass, light from even more distant early places gets here. That makes the edge move outward for us. At the same time, there is a different edge. If a galaxy too far away sends out a beam today, the stretching of space can make that beam never reach us. That is the event horizon. So yes, one edge moves, one edge does not. Neither is a wall you can crash into. Let me give you a timeline feeling. The universe spent a tiny fraction of a second in a super fast growth spurt at the very beginning that set the stage. After that, things cooled. About a few 100,000 years in, space turned clear, and that microwave afterglow took off. Hundreds of millions of years later, the first stars turned on, bathing the universe in harsh light that stripped electrons from atoms again for a while. Galaxies assembled, black holes swallowed gas and lit up as bright cores. By a couple of billion years in, the universe was busy, building the big structures we see now. What NASA's pulling in with those deep fields are snapshots from the first steps in that build, and some of those steps look faster than the recipe said they should be. And no other audio segment you can use, even if the screen is just my face. When I say deep field, picture a star field where most points are small, but a few look stretched and red. I will tell you which ones are likely foreground and which are background based on color and shape. Blue and sharp is usually closer. Red and diffuse is usually farther. When I say lensing arc, I will tell you it looks like a thin banana of light near the cluster core. When I say dropout galaxy, I will explain that the object appears in some filters and vanishes in bluer ones, because its light has been pushed out of that range by expansion. So if you are only listening, you still track the logic. There is also this question: if distant galaxies are receding from us faster than light, how can we see them at all? Here is the trick. The light we are catching left those galaxies when they were much closer. While the light was on the way, space expanded and carried those galaxies away faster and faster. But the light had already been launched into our future light cone, and it kept inching toward us as the expansion rate changed over time. Again, nobody broke the rules. You have to keep two speeds in your head: local motion through space and the rate space stretches. People also ask if we are at the center, because it looks like everything is moving away from us. We are not special. Every point in an expanding universe sees the same pattern. Take a rising loaf of raisin bread. As the dough rises, every raisin sees the others moving away. No raisin is the center. That is a good kitchen-level picture. And no, you do not need to see a diagram for that to click. How about this phrase, broke physics? It is fun to say. It is almost never what is actually happening. In practice, it means the data is telling us to adjust a parameter, or to add a piece we suspected might matter, or to think harder about our biases. A telescope is like a truth machine with a personality. It shows you what is there, but it also shows you what your assumptions hid. The first time we looked really deep with a new kind of eye, we found more than we expected. That is the whole story of astronomy. Every time you push a boundary, the universe says, here are 10 more puzzles. Now let us address a thought that sneaks in when you hear about edges and horizons. People feel a little boxed in, like there is a huge amount of reality we are cut off from forever. That is true in one sense, and not a reason to be sad. The piece we do see already holds everything from particle physics to black holes to life, and the rules we infer here look like they apply out there, because the snapshots we do get line up. The baby picture matches the adult picture when you evolve the model forward. That is a crazy level of coherence for one species of primate. With a telescope, oak, concrete takeaways you can walk away with. Number 1, there is no hard wall at the edge. There is a horizon set by time and by expansion. Number 2, NASA did not break physics. The new image forced some tweaks in our early formation timeline because we saw more early heavy hitters than we predicted. Number 3, the edge moves for us because new old light arrives, while a different boundary defines which places we can never talk to, even in principle. Number 4, you do not need the picture in front of you to follow the argument. If I say lensing, I will tell you arcs. If I say high redshift, I will tell you very red faint smudges that drop out of the blue filters. If I say microwave afterglow, I will tell you it is the oldest light, seen as tiny temperature bumps across the sky. Does any of this change your day? Maybe not, but it changes how you think about where you are standing. You live on a rock that can read the first pages of the universe. That is not poetry. That is what we are doing when we look at those fields. We are reading those little dots are timestamps. The ones that look too mature too soon are telling us our chemistry and gravity got rolling fast. The so-called edge keeps stepping back, because the story keeps coming in. Let us run through a few common traps so you do not fall into them when the next headline drops. Trap 1, thinking the edge is a place you can fly to. It is not a location with a door. It is a limit in time and light. Trap 2, thinking faster than light talk means someone cheated relativity. It is the yardstick that is stretching, not the ruler sliding past the speed limit. Trap 3. Thinking a surprise means everything is wrong. Surprises sharpen the picture. They do not throw out the whole camera. Trap 4. Believing that if you cannot see the picture, you cannot follow the science. A good explanation works in audio. You just need the shapes in your head. Arcs mean lensing. Red faint means distant. Missing in blue filters means super distant. A sky-wide faint glow with tiny ripples means the oldest visible light. Now what would really count as a discovery that changes chapters? An unambiguous signature of the first stars turning on isolated and mapped. A clear pattern that says primordial black holes formed in the very early universe and seeded the big ones we see now. A direct detection of waves in the oldest light that point to that first wild growth spurt at the beginning. Any one of those would not break physics. It would lock in parts of the story we only sketch right now. Some of you will say, okay, but what about beyond the edge? If we cannot see it, why talk about it? Fair. The only reason to talk about it is because The part we do see follows rules that you can evolve. The math says, if space is flat to an absurdly good approximation on the largest scales we can measure, then either it is infinite or it is so large that any curvature is beyond our patch. If you are asking about what happens beyond our horizon, you are already out on a limb. We keep a light grip on those branches. Let us return to the image that started this conversation and do one last audio pass so you can carry it around in your head. Start with a black field scattered with points. Nearby stars are bright and spiky because of the telescope optics. Ignore those. The real story is the soft, tiny reddish dots. Some look like little smears, some like barely there embers. A cluster in the middle makes subtle arcs. Those arcs tell you there is a heavy mass bending light near those arcs. Right at the limit of detection are the most distant candidates. They are bright enough to register because the lens is helping. They live at a time when the universe was still getting transparent and clean, and yet they carry the signature of built systems, not just single stars hearing that. You understand the line people mean by broke physics. It really means our recipes for early construction were too slow. We speed them up and keep going. Big question, if the edge moves, what will we see next year that we cannot see now? The answer is more of that early build, with better confirmation, better spectra, and cleaner distances. One by one, candidates turn into solid points on the timeline. We will map the first generation of stars, not by seeing individual suns, but by reading the pattern they left on the gas around them. We will watch black holes shine when they gulp gas in the young universe, and we will get a sense of how many there were. None of this requires a miracle. It requires time on the scope and careful work. And because the horizon is a time boundary, not a wall, every year buys you a bit more reach. You might be wondering if the edge moving outward means some galaxies will slide out of view forever. That is the other horizon at work. There are galaxies we can see today because the light we are catching left them long ago, when they were closer, but light they are sending out right now may never reach us. In the far future, our sky will get emptier as expansion carries distant systems out of our forever view. That does not have to be sad. It is a reminder that cosmic time has chapters. In this chapter, we can still read almost the whole history of the visible universe if we build the right tools and keep our eyes open. Last piece. What should you say when someone hits you with, "We found the edge of the universe, and it is moving"? You can say this without losing anyone. The edge we found is the farthest light that has reached us so far. It seems to move because new old light arrives as time passes. The image did not find a brick wall. It found very early galaxies that look more grown up than expected. That pushes us to adjust how fast stars and black holes formed at the start. Space itself expands, so distant galaxies are carried away by the stretching of space. That allows effective speeds faster than light without any rule being broken, because nothing is outrunning light locally. There is also a different horizon that marks the farthest places we could ever hear from. No matter how long we wait, both edges are real. Neither is an end of everything. I will keep the descriptions audio-friendly every time I mention a picture. Deep field means a sky patch full of faint red smudges that are entire galaxies. Lensing cluster means a heavy knot in the middle with curved arcs around it. Microwave afterglow means a sky-wide pattern of tiny temperature bumps that tell us what the baby universe sounded like. You do not have to see the pixels to understand the message. So did NASA find the edge? They found a new far page of the story, and the reason it feels like an edge is because our eyes just reached it. Is it moving? Yes, in the sense that patience brings us more ancient light, and the map of our observable universe keeps growing. Did the image break physics? No. It broke our lazy assumptions, which is what good data is supposed to do. That is the clean version. No hype, no secret wall. Just a bigger horizon, a faster early build than we guessed, and a universe that keeps rewarding anyone willing to look longer than feels comfortable. If that is breaking anything, it is breaking our habit of thinking we were done learning. And honestly, that is the best kind of break there is.